Hello everyone. Today we'll study the limits and continuity of multivariate functions. In this section, we'll discuss the following questions. First, how to define the limits of multivariate functions. Second, how to understand the limits. Third, how to define the continuity. On studying the contents of this section, we should compare the similarity and difference between the limits of one variable and multivariate functions. We firstly recall the definition of the limits of one variable function. Its intuitive meaning is the values of f(x) get closer and closer to L as x approaches A. We can describe them by mathematical inequalities. F get closer and closer to L means this inequality holds, and x approaches A means the distance of x and A is larger than 0 and less than some delta. So its epsilon delta definition is as follows. The limit means that for each positive number epsilon, no matter how small, there is a corresponding delta larger than 0, such that the abstract of f(x minus L) is less than epsilon, provided that the abstract of x minus A is larger than 0 and less than delta. Based on the above review, we can easily extend the definition to the situation of multivariate functions. We considered the bivariate function z equals fxy. The usual intuitive meaning is the values of fxy get closer and closer to L as xy approaches AB. Similarly, we can describe them by mathematical inequalities. fxy get closer and closer to L means this inequality holds, and xy approaches AB means the distance of xy and AB is larger than 0 and less than some delta. Thus, we have the following definition. F converges to L as xy approach AB means that for arbitrary positive number epsilon, no matter how small, there is a corresponding positive number delta, such that the abstract of fxy minus L is less than epsilon, provided this inequality holds. To interpret the expression, just think of xy and AB vectors, then we have the following expression, and all the points satisfying the inequalities are those points inside a circle or radius delta, excluding the center AB. Recall that this set means the neighborhood in R1. Similarly, the next set is called the neighborhood in R2. Now we give the definition of plane neighborhood. Let P0 is a point in R2 and delta be a given positive number. The following set is called the neighborhood of the point P0 with radius delta, sometimes simply as UP0. Obviously, the points in this neighborhood are all in the circle of center x0, y0 and radius delta. If the center of this neighborhood is removed, then the set is called punctured neighborhood, denoted by this notation. We need to note several aspects of the definition. Firstly, the behavior of fxy at AB is irrelevant. The function does not even have to be defined at AB. This follows from this restriction. Second, the path of xy approach to AB is irrelevant. The directions of xy approach to AB are numerous, and the paths are also diverse. If we denote rho, the distance between P and P0, that is, rho equals this expression, then no matter how complicated the process that P approach P0, we can use rho approaching 0 to represent the process P approaching P0. Then we have the following definition of limit. Definition: let the domain of fxy be D, P0 be an interior or boundary point of D, and L be a constant. If for arbitrary small positive number epsilon, there exists a positive number delta, such that for all points xy satisfying the following expression, the abstract of fxy minus L is less than epsilon, then L is called the limit of fxy as xy approach AB. We denote the limits by the following notations. Note: the definition is phrased so that it immediately extends to functions of 3 or more variables. Simply replace xy and AB by xyz and abc. And we also use the latter two expressions to delete them. Just regarding P and P0 as points in R3. Then, what's the similarity and difference of the limit definitions between the functions of one and several variables? On one hand, according to the epsilon delta definition, they have the similar formal definitions. On the other hand, for the approaching with in the limit definition of one variable function, there are only two ways that x approach A, but in that of multivariate functions, there are infinite ways that xy approach AB. This is the essential difference between the limits of one variable and multivariate functions. We might expect that limits for many functions can be obtained by substitution. This was true for many functions of one variable. This method is also valid for polynomial and rational functions in the variables x and y. The polynomial is a function of the following form, and a rational function is the quotient of two polynomials that is this form, where both p and q are polynomials and q is not identically to 0. We have the following theorem. If fxy is a polynomial, then the following expression holds. Fxy converges to fab as xy approach AB. And if fxy is a rational function, then we have the limits as follows. Furthermore, if the limit of P is L and L is not equal to 0, and the limit of Q is 0, then the following limit does not exist. Note, this theorem shows that the substitution method is valid for polynomial and rational functions in variables x and y, which is an analogous to theorem 1.3b. Now, let's evaluate some limits if they exist. Example 1. It is often easier to analyze limits of bivariate functions, especially limits at the origin, by changing to polar coordinates. So, for A, by changing to polar coordinates and Hospital's rule, we have the following expressions, and the limit is 1/3. For B, again changing to polar coordinates, we have the following expressions. Since this limit depends on theta, different straight line passes to the origin will lead to different limits. Thus, the limit does not exist. Question: is there any other idea? Method 2. The idea is if different passes lead to different L values, then the limit does not exist. So let y equal kx, then the value is k/1 plus k squared. Since this value depends on k, different straight line passes to origin will lead to different values, so the limit does not exist. Example 2. Try to find the limit. Solution: by changing the function, we have this expression. Replacing x squared y by u, the limit for bivariate function can be expressed as limits for function of just one variable u. So the limit of the first term is 1, and the second term converts to 0 from the following inequalities. So the limit is 0. Example 3. Try to find the limit. Solution: rationalize the denominator. We have the following expressions. So the limit is -4. Similar to the continuity of one single variable function, if the limit of f equals the functional value of some point, then we call f is continuous at this point. We have the following definition. Let B be the domain of f, P x0, y0 be an interval or boundary points. If the following expression holds, then it is called f is continuous at P0, and x0, y0 is also called the continuous point of fxy. Furthermore, if the function fxy is continuous at each point over the open set or closed set D, then it is called fxy is continuous over D, or called fxy is a continuous function over D. Remarks: 1. Theorem A shows the continuity of polynomials and rational functions. 2. Furthermore, sums, differences, products, and quotients of continuous functions are also continuous. 3. These results, along the next theorem B, can be used to establish the continuity of many functions of two variables. Now we give the continuity of composite functions. Theorem B. Let g(xy) is continuous at AB, and one variable function fu is continuous at GAB. Then the composite function fg is also continuous at AB. The proof of this theorem is similar to the proof of theorem 1.6e. Example 4. Let fxy is defined as follows. Prove it is continuous in XOY plane. Proof: when x squared plus y squared is not equal to 0, note that fxy is an elementary function, so when xy is not equal to 0, 0, the function is continuous at any point xy. Next, we show that fxy is continuous at the origin 0, 0. Since the function sin u is bounded, so we have the following inequalities. Note that the right term converges to 0 at xy approach 0, 0. So the limit of f is 0 and is equal to f0, 0. So f is continuous at the origin. Thus, fxy is continuous at each point in XOY plane. We studied the mixed partials in the last section. For bivariate function fxy, sometimes the mixed partials are equal, sometimes they are not equal. Based the continuity and inequality of mixed partials is simply stated as follows. Theorem C. If fxy and fyx are continuous on an open set S, then they are equal at any point of S. Next, let's make a summary of this section. Today, we learned the definitions of limits and continuity of multivariate functions and two theorems B and C. We should understand the similarities and differences between the limits of functions with one variable and more variables. Thank you for listening. See you next time.